Hello and welcome back to this course on computer organization. So now we are going to look at the pipeline processes performance. Okay, so we are as usual going to look at the program execution time of a given benchmark circuit, right? So let's go back to the same example that we had used earlier, assuming that there are 25% loads, 10% stores, 13% branches, 52% register type. But now there is one small additional complication. Apart from knowing the histogram of different types of instructions, we also need to know how many of this, in the sequence of instructions, what fraction, okay, of loads are used by the next instruction. Remember that, with register forwarding and all that, we were able to prevent stalling of the pipeline significantly, right, for a lot of cases. But for the load word, we had no choice, we had to stall the pipeline, right? Therefore, we are saying that 40% of those loads are being used by the next cycle, by the next instruction. That means you are trying to load into a register and use that immediately. Therefore, there is no choice but to stall for one additional cycle there. Okay, basically all of this is going to affect your cycles per instruction, right? Also, 50% of the branches are mispredicted. That means you are assuming that, okay, the branch is not going to be taken. You prefetch and keep everything, but 50% of the time the branch may happen, and therefore you have to end up flushing, right, those two instructions, and then you start, all the way from fetching of the next instruction after the branch is taken, right? So what is the average cycles per instruction now? That's what we want to calculate. Ideally, it should be 1. Every clock cycle, one instruction, if you wait for 5 clock cycles initially, the first instruction will complete. But after that, every single clock cycle, the output of the next instruction is available. So ideally, the cycles per instruction should have been 1. Okay, though it is a multi-cycle, kind of execution here because of pipelining. So the point is that for load, right, the cycles per instruction is 1 when it is not stalling, but it is 2 when you are stalling, correct? Because you are ideally, if the load destination register is not being consumed by the very next instruction for a register read, right, then things can go on normally. There is an extra cycle available before that result is consumed. However, if it is indeed consumed, right, then you need 2 cycles for you to complete that load. You have to stall 1 extra cycle. So the cycles per instruction for load word is the fraction of instructions which, where the loads are not used by the subsequent instruction, right? Then that is 60%, because we have said that 40% of the instructions actually of the loads are used by this very next instruction. Therefore, 60% don't use it, in which case it is 1 clock cycle for the load instruction that has to be executed. Otherwise, it is 2 clock cycles with 40% of that instruction. So therefore, the cycles per instructions on average for load word is 1.4, right? Now, branch, CPI, cycles per instruction, when it is not stalling, right, when the branch is not taken, then it is just 1, right, because everything is going on as expected. You have prefetched, anyway that path is correct, you proceed. But when the branch is taken, you have to flush those two cycles before, right, 2 instructions you have to flush out and then start all over again, and therefore you will end up taking 3 cycles to actually sort of to complete the branch on equal, right? So therefore you are going to take 1 cycle when the branch is not taken, and 50% of the instructions are, branch is predicted correctly, and 3 cycles when you are actually not sort of completing the not taking when you are taking the branch actually, right? So let's go this back and look at this timing diagram here. So if you look at it, when the branch is taken, right, like I said, the next instruction execution should have happened right here in cycle 4, right? But it is taking 4, 5, 6 additionally, right? So that's why that's the 3 cycles that we are actually talking about for the branch when it is mispredicted, right? Or the branch is taken appropriately. Okay. So therefore, if you look at this, we are now talking about the effective cycles per instruction for branch is 2. For cycles per instruction for load word is 1.4, and therefore I can now define an average clock cycles per instruction for this particular distribution of different types of instructions, this particular histogram, right? So I am saying 0.25 into the load, okay, this is 1.4. Then I am saying 10% stores, and that is all other instructions basically just take 1 clock cycle, right? R type and all basically takes 1 clock cycle because of register forwarding unit that we have done there, we have put in there, okay? Otherwise that also could take more cycles, by the way, right? So 13% branches, right? So that is what we are doing here into 2, so average CPI. For the load it is 25% loads into 1.4 cycles, and then 52% R type into 1, of course, right? So this is the 10% store taking 1, and therefore you get a average clock cycles per instruction to be 1.23. okay. Now this is very nice, ideally it should have been 1, but we have made it 1.23. but the biggest advantage now is that we can speed up this clock cycle significantly, right? So therefore what we now need to do is to figure out what is the critical path and what is the frequency that is going to determine the period of this entire pipelined processor, okay? So for that reason, let's just come back here, okay, and let's just take this pipeline processor, okay? So I'm going to make a copy of this into my, yeah. So now what we are going to do is to figure out what is the clock frequency at which this pipelined processor can work, okay? So first of all, what we did was we started with a very big combinational block in the single cycle processor, which did fetch, decode, execute, memory read, then write back, and so on. And we broke this up into smaller stages and by putting flip-flops in between them, okay? So effectively in the single cycle processor, we said that the critical path was for the load word instruction, where the launch flop was a program counter, and then you wrote back into one of the destination registers after doing the memory read at the data memory, okay? So that's why that was the critical path. So the launch and capture flop had a lot of combinational logic in between them. So what we are going to do now is to simply come and look at the various stages, okay? So we already have broken this into many different stages. So this is the fetch, right? And this is the decode, right? This is the decode, then this is my execute, right? Then this is my DMEM, data memory, okay? And finally we are back here for the register RF write back stage, okay? So remember from our static timing analysis, when we discussed pipelining for combinational circuits, we said that the clock frequency of the pipeline system will be determined by the slowest combinational stage between any launch and capture flip-flop, right? So therefore what we are going to do is, first of all, we are going to identify the critical path in each of these stages, okay? So I am going to go ahead and look at this whole thing, okay? I will write this out. Stage, okay, my capture flop, no, this is launch flop, capture, okay. Okay, so just let's put that down first. Okay, so what is this? We are looking at fetch. Okay, the fetch is obviously going to be controlled by this program counter flip-flop, right? That is what is going to come through that. So your program counter is going to launch and it will get captured by which flip-flop? I will call this FF1, okay, FF2, FF3, FF4. Right, so we have put 4 additional flip-flops in this pipelined processor. So therefore, the capture flop is FF1. Okay, and now what is the critical path that is basically going to determine this whole thing? So if you look at it here, there are 2 different paths. One, you are going through this data memory and then coming here. Additionally, there is another interesting path which is going through this adder, okay, and it is coming back through this mux to this program counter itself. So I'll remove this highlight. So there is one path there, but that's just going through one very small adder and it's not a full-fledged ALU, it's just an adder. Okay, so the delay will be much smaller than the ALU and you're just doing +4 and then bringing that data back. So there is a path which is starting from the program counter. Launch flop is program counter, going through just an adder, one multiplexer and coming back to the program counter. So that is also there, but that is going to be a very short path. In fact, it is that kind of a path where you have to worry about the whole time. Remember, I told you that you design for the slowest path, but beware of the fastest path. That is the fastest path that you will have to worry about. Okay, and if it is not slow enough, you need to add buffers or something like that. You need to add a couple of inverters in the path. Anyway, so therefore, the critical path for this fetch stage is obviously originating from the program counter, giving the address to the instruction memory. You are reading that out into onto the data bus of that memory, RD bus, and then you are putting a flip-flop out there. Therefore, really the capture flop is this program, the FF1 flip-flop. Okay, so the path in magenta is what I would call the critical path here. And if you look at the timing diagram for this, right, if you look at it, data has to, the clock goes high, then the program counter, what was in the program counter gets read into past the flip-flop into this PCF bus wire, okay, and that will take a TPCQ delay. Okay, so let me just draw that here just only for one stage so that you understand and recollect this. I'll just draw the clock here. Okay, so this is what I have. My program counter, which is basically this, the PC, right, which is just before that flip-flop. I'm going to call this as PC. Okay, was already ready with the next instruction. Okay, assuming that is some PC plus 4. Okay, this was the earlier PC. So then the PCF is going to go past this, it will take some time to get stabilized, and this delay is what we are going to call as T TPCQ delay. Okay, TPCQ delay, then that data will go, address will go into the instruction memory, it will fetch it and will appear on the RD bus. Okay, well, after the TMEM. Okay, so that is what is going to happen here. So the input of flip-flop 1 will see the data stabilize TMEM after PCF. Okay, so if you want me to just, maybe I'll move this up here a little bit so that I get some more space, right? I'll put that here. So if you look at the signal out here, right, I will call it INSTRF in the fetch stage, INSTRF, right? So this is the time that it will take, right, and things will start changing very quickly, and it will take some time for you to read, and this is the time that we call TMEM. Okay, and of course on the next clock edge the FF1 flip-flop has to capture this, and therefore you have to set this up T setup before, right? So this is the critical path for the fetch stage, and therefore the delay that we are going to talk about, right? If I just put that here, I will talk about the critical path delay, right? I will just say in magenta TPCQ plus TMEM plus T setup, right? This is what we have for the first stage, for the fetch stage. Now what happens when we go to the decode stage? Okay, the decode stage, the launch is now going to happen from flip-flop 1. Therefore this is my launch flop. Okay, and then the instruction D, INSTR D, is the output of the flip-flop 1. So on the next cycle, if you look at INSTR D, right, this is my second clock cycle, right? If you look at this, this is, so let's say that it has obtained instruction 1 out here. Okay, so this, this whole thing will be unknown in this period. I have no idea what it is, so I will not, right? And it will take some time for this to settle. And what is that time? That again is TPCQ. Okay, the instruction D will be ready. Which instruction is this? It's the same first instruction that you have fetched in the previous clock cycle in the fetch stage. That is coming out into the next clock cycle in instruction D. Now instruction D is available. It is going to go through the register file. It's going to go through the control unit, right? It's going to go through the extended, the extension unit, right? So therefore, what is going to happen is you are going to have many different paths which will get exercised. Okay, so let me mark a couple of paths. First is this path, right? Then there is a second path here, right? Then there is a third path which is going to come, let's say, through this guy, through the control unit, right? This whole, so this thing will come in, then it will come through the control unit. So this will be ready, T decoder or T controller, whatever, T decoder after that, right? Remember this signal would have arrived just TPCQ after that, after the clock edge, right? While the T decoder is of course larger, so therefore this is another interesting path. So it will take T decoder plus T extension unit is one delay, right? Then there is the T register file whole, T PCQ delay is common to everything, whether you go through extension or what, it doesn't matter, right? So really all these signals will arrive at the control block, register file and extension unit T PCQ later. Okay, so therefore I am now only going to worry about three different paths. Okay, one is through the register file in magenta, through the register file in orange, or this purple path which is going to go through the extender, right? Clearly the register file delay will dominate, and therefore that is what we have to worry about, and that will be the critical path, with the capture flop being flip flop 2. So this will again be TPCQ plus T register file read plus T setup, because after the register file read you have to set it up before the next clock hits for flip flop 2 to capture appropriately, right? So now I come back to the next stage, which is execute. Okay,